This is part 2 of my summary of the Deep Learning book, authored by Ian Goodfellow and others, as presented on screen here. I recommend watching previous videos in the series if you haven't yet. This is a multi-part project to work through the book from the beginning and make sense of and hopefully be very proficient with the subject matter by the end of it, having started as a complete newcomer. So, this is the overview for the contents of part 1 of the book, which encompasses multiple chapters. So these will obviously be split over a number of videos, and as discussed in the introductory video, I will work through these sequentially. And with regards to the math and everything else, having completed my undergraduate, I'm using my knowledge as the barometer for how much should be presented in these videos. So we're not starting from complete scratch and learning every little bit that there is to learn, but where I encounter something I don't know, I'm going to dig into it until I feel very comfortable with the subject matter. Alright, so getting right into it, part 1 begins with chapter 2, covering linear algebra. So as an FYI, the authors recommend that those with no prior exposure to linear algebra consult further resources. The chapter focuses on the math most important to deep learning. The image here comes from a YouTube video by 3 Blue 1 Brown, for which I'll share the link in the description. In his video introducing a series on linear algebra, he cites a common problem in education systems, which is that computational methods are taught without the motives and intuitions behind those methods being adequately explained. To some degree, my own education in linear algebra felt that way, so I'll be doing my best to present my own video presentations in such a way as to avoid that. I want to be try and get to the intuitive heart of things as much as I can and make it clear. This may or may not entail a significant degree of quoting from the textbook or other outside sources. My goal isn't to provide a comprehensive education in linear algebra, but just to refresh myself on and understand the fundamentals. So this is the author's stated goal as well. Alright, so just a quick review of the basic tools. When it comes to scalars, they can pertain to various sets, such as complex numbers, integers, real numbers, etc. More examples of the notation, the specific symbols used, can be found on the wiki link in the description. When it comes to vector notation, the reason that the set of numbers to which the matrix elements pertain is raised to a power is because the vector is said to be lying in the set formed by taking the Cartesian product of r n times. So that's why we see r to the n. The way I think of that is that you have a number lying as being one set of real numbers. So when you have multiple of them intersecting in a vector, you're thinking about the vector as being a point in n-dimensional space if the vector has n elements. So the following tools are really just extensions of one another, you might think, that way at least. You can think of a matrix as a collection of vectors against one another, and a tensor as the result of layering multiple matrices against one another. So it's like a matrix with more than 2 dimensions. Transposing the matrix just means flipping it along the diagonal, which people might be familiar with from spreadsheet applications. Addition is straightforward, you just add elements at the same indices to each other. Same with multiplication, for which the example is given. The authors specify broadcasting as an atypical matrix operation used in deep learning. So you see an example there. So matrix multiplication as a function, as an operation, is only defined for 2 matrices, where the first has the same number of columns as the second has rows. If that isn't the case, 2 matrices cannot be multiplied. So on the left is a very quick summary of how to multiply matrices, and for more details you can see the link in the description. There are lots of resources for that online. I would recommend checking it out if matrix multiplication seems unintuitive or nonsensical, as that webpage shares a good example for why it's done that way. On the bottom right, you'll notice that matrix multiplication is distributive and associative, but not commutative. Very important to understand the properties of it. So one of the classical applications of matrices is to represent a system of linear equations, as we can see here, in a form where you have some set of variables being multiplied by different constants in different equations to yield some scalar. It can all be bundled up into a single matrix equation, a small matrix equation, which is easy to write out and it's compact. So that's the kind of thing that we see at the top of the slide. We see a matrix representation of an entire system of equations. So being able to express something using a highly condensed shorthand is great, especially if no loss is there due to compression. loss of information, but the real power of the matrix perspective is that it provides a means for solving the system as well as expressing it. So linear systems can be solved by making use of the inverse matrix and the identity matrix. An identity matrix is simply a matrix that only has ones across the main diagonal and zeros everywhere else. The characteristic property of such a matrix is that when you multiply it with a vector, the result of the multiplication is the same vector that you multiplied it with. The inverse of a matrix is the matrix that, if multiplied by it on the left, the result would be an identity matrix. The reason it has to be on the left is that matrix multiplication is not commutative. So the concept of the right inverse exists, but the matrix itself would actually be different. The right and left inverses are not the same. So I'd recommend the YouTube series by 3 Blue 1 Brown to see some really fantastic visualizations on this topic. He describes how a matrix is actually a transformation, a linear transformation. And so the inverse is simply the reverse of the transformation. It's really fantastic animations there to make intuitive sense of this, so I'll put a link in the description to that. So once we have these mathematical tools, it's a relatively simple process to solve for the arguments, x, in our the unknowns in our linear system. So we represent them collected into a vector form. So by multiplying both sides of the equation by the inverse of the coefficient matrix, you end up with a column vector of the variables that you want on the left side, and matrix multiplication on the right side. Since multiplying a matrix with a vector yields a vector, we know that the right-hand side reduces to a single vector which will have the solutions that map directly onto the variables of interest. So solving this situation depends on the possibility of determining what A inverse is. So we'll discuss that now. The existence of the matrix inverse is not guaranteed. When it exists, there are different algorithms to compute it, but the authors don't go into more detail, as they suggest that there are alternative ways of computing more accurate answers on a computer, but this is still an important theoretical tool in linear algebra. So having said that, for the matrix inverse to exist, there must be only exactly one solution for any values that the vector b takes on. That is the case when the vector b is in the span of matrix A. So to understand this, consider the outcome of the matrix multiplication of A and X. The math is analogous to a situation where the matrix A represents 3 different vectors. In this example, because there are 3 columns, and those vectors are being multiplied by distinct sizing factors, represented by the X values, and then summed. This can be illustrated if we consider each row of the matrix as representing the size of each column vector in a different dimension. Now if you consider the b vector as being a point in space, the question becomes whether or not there exists some sizing factors, the x variables, for those vectors, the column vectors, such that the combination of those 3 vectors at that particular sizing factor for each could reach the point indicated by b. So from principles of linear algebra, we know that n linearly independent vectors can span an entire n-dimensional space. For example, you can reach any point on a 2D Cartesian grid with only the x and y unit vectors, because they're linearly independent. Given this principle, we know that the A matrix must have at least as many columns, i.e. vectors, as B has dimensions, i.e. rows. So that creates one condition under which we can solve for A inverse. But as with the example of the x and y unit vectors, the basis vectors we have, in this case the column vectors of matrix A, must be linearly independent of one another to be able to reach any point in the n-dimensional space. So that is our second condition, that the columns be linearly independent. Finally, we need this system to be such that there is at most one solution for each value of b. In our case, there are 3 dimensions. That means that if we had more than 3 linearly independent vectors to choose from, we could construct more than one set of basis vectors to reach the point denoted by b. For example, if we had 4 columns in A, we could use the column vectors of 1, 2, and 3, or we could use the column vectors of 2, 3, and 4 to construct our basis of 3 vectors to reach that point. So that scenario would not be valid because we would have multiple possible solutions to reach b. Therefore, our final constraint is that the A matrix must have at most a number of vectors, i.e. columns, equal to the dimension of b. so in our example 3. I've linked a video which provides really great animations of these principles again, which can help aid in understanding, so I recommend checking it out if it's not clear. So together we have 3 constraints on the nature of the matrix A such that an inverse exists for it. Constraints 1 and 3 can be simplified by saying that A must be a square with dimension equal to the B vector. The characteristic describing the kind of matrix that fits these conditions is that it is singular. You should know that if A is not square or singular, there's still a solution, but this A inverse this particular method cannot be used to get at that solution. So, moving on, norms are a means of measuring the size of a vector. Multiple norms exist. These are different ways you can measure the size of the vector. So the Euclidean norm is one to know. It's an LP norm with p equals 2. And the authors mentioned that it is used so frequently it's sometimes written as just x with double bars, with the subscript 2 omitted. A different norm is also used often, which is the squared L2 norm. So it's just the L2 norm, except with the outcome being squared. In cases where it's important to discriminate between 0 and non-zero values, the L1 norm is used, since by not raising very small values to an exponent, the outcome is maximized, as opposed to when those small values get smaller when squared, such as happens with the L2 norm. So sometimes a norm is used which is the sum of non-zero elements in a matrix, but this is not an LP norm. The authors mention the L1 norm is often used as a substitute. There is also a simple concept of the max norm, which is equal to the largest element in a vector. For matrices, the Frobenius norm is used, which is similar to, in computation, to the L2 norm. So moving on, the identity matrix we saw previously is an example of a diagonal matrix. But in general, a diagonal matrix could have any numbers along its diagonal, so long as those numbers are the only non-zero elements. Taking the diagonal of a vector means creating a square diagonal matrix with the elements of that vector along the diagonal. One key feature of diagonal matrices is that computing their products is a much less intensive process than doing so for non-diagonal matrices. And while diagonal matrices can be rectangular too, no inverse would exist for a rectangular diagonal matrix. A special case of orthogonal vectors is when they also each have unit norms, in which case they are orthonormal. As per the description presented here, orthogonal matrices are actually orthonormal as well, even though they're referred to as just orthogonal. They are of interest because it is very easy to compute what the inverse for such a matrix is. So we can take a look at these examples to make the definition clear. So looking only at each of the rows in a given matrix, the vectors created by those rows are linearly independent. So we see, for example, we have this matrix where if we look at the row, we see 1, 0, so that's a vector, 1, 0, and the next row is 0, 1. So these vectors considered separately, well, they're linearly independent because no multiple of 0, 1 will ever reach the vector 1, 0, and vice versa. Then if we look at the columns created by this matrix, we have 1, 0, and then 0, 1. So it's the exact same situation. No multiple of the vector 1, 0 will ever be able to reach a point specified by the vector 0, 1. So these column vectors as well as row vectors within this matrix are all linearly independent. Row-wise, the vectors are linearly independent, and column-wise, the vectors are linearly independent. And so it is orthogonal. Similarly, we see here that this four-dimensional matrix has, basically you could consider it as having a vector for a unit vector in each of the 4 dimensions. So we have 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 0, 0, 0. And so if we just look at it from the sideways perspective, we see that the exact same collection exists. It's in a different sequence, but fundamentally the vector collection is the same. And so obviously, since these are all unit vectors in different dimensions, they're all linearly independent. And so this entire matrix is orthogonal, as row-wise all vectors are independent, and column-wise all vectors are independent. And lastly, this example using trigonometric function shows that the vectors row-wise collection of vectors and the column-wise collection of vectors need not be exactly the same for this to be true as well. So the next topic is eigendecomposition. Eigendecomposition is the process of decomposing a matrix into a set of eigenvectors and eigenvalues. So considering a given matrix A as communicating a transformation of vector space, an eigenvector for matrix A is a vector that, after being transformed, would simply be stretched as compared to its original form. That is to say that it would be a scalar multiple of what it was before the transformation was applied. That scalar multiple, the stretch factor given by the transformation of matrix A, is the eigenvector's eigenvalue. If a matrix has even one eigenvalue, it can have infinite eigenvectors that are all different length in the same direction. So we simply refer to the unit eigenvector for a given direction. Different eigenvectors can have different eigenvalues or the same eigenvalues, depending on the matrix transform applied. A fantastic video series making use of the animations really helped me to understand these concepts, so I've shared a link to that in the description. I highly recommend you check it out. It's the same one I've mentioned previously. I've created a simple illustration on the bottom left here, on the bottom right rather, to make sense of it. So imagine that the black arrow is your vector, and on the left side it hasn't been transformed in frame 1, and in frame 2 the transformation of a matrix A has been applied. So also imagine that the red and yellow vectors are two eigenvectors for matrix A with their own eigenvalues. So to find our vector, again in black, after transformation, we have two approaches. First, we could perform matrix multiplication of the transform A with our vector, which could be computationally costly. Alternatively, we could consider our vector as being composed of some combination of the two eigenvectors. So you could see that visually, where the eigenvectors, when placed head to tail, reach the point specified by the black vector. So once you've decomposed it in such a way, then the entire transformation involves nothing but multiplying those two vectors, eigenvectors, by their associated scalar eigenvalues. The big idea is that if the component elements of the equation are known, namely the eigenvectors, their inverses, and their eigenvalues, then this method is very easy to do computationally. In this example, you see that the red eigenvector's eigenvalue has to be less than 1, as the vector got shorter after the transformation. And the yellow eigenvector's eigenvalue was something like -1, as its direction changed and it flipped around. Once again, I recommend watching the video I've linked in the description for really great animations of these transformations. So here's a long run-on sentence describing this somewhat more technically. The eigendecomposition of a matrix is basically the notion that the transformation in space that a matrix represents is equal to the transformation that results if you convert your object in question to the form in which it would be represented using eigenvectors as a basis, which would be enacted by the multiplication with the inverse eigenvector matrix, stretch that vector, which would be done by multiplying it with the diagonal lambda matrix or eigenvalue matrix, and then convert that eigenvector basis form back into your original basis, which is done by multiplying it by the eigenvector matrix once again. Importantly, not every matrix can be decomposed into eigenvectors and eigenvalues. Sometimes it can be done, but the computations involve complex numbers. For the purposes of this book, we only need to decompose a specific class of matrices that have a simple decomposition. So the following expression is true when the matrix in question, matrix A, is composed of real numbers and is symmetrical. In this situation, the existence of eigenvectors is guaranteed, but the eigendecomposition may not be unique. This refers to the possibility that there may not be a number of distinct eigenvalues equal to the number of dimensions in the diagonal matrix. The question is how many eigennumbers there are, as opposed to eigenvectors, because each eigenvalue can have infinite eigenvectors associated with it, but all eigenvectors corresponding to the same eigenvalue are linearly dependent to one another. So, for eigendecomposition to be unique, there needs to be n unique eigenvalues for an n-sized matrix. Under that condition, the span of the linearly independent eigenvectors is the entire n-dimensional space. So any vector in the n-dimensional space could be successfully decomposed into a combination of the eigenvectors. At this point, I'm going to end this presentation to continue the next one with section 2.8 of the Deep Learning book. Thanks for watching, and I hope that this may prove useful. Take care.